Yay!
Yay! All right, one more little piece that we have to do for work and energy is what happens if it's a non-constant force. So far we said already, if you want to say work is force times distance, that's kind of all right, but you got to be careful because if it's not going in the same direction as the displacement, then it's force dot product with the displacement. But even that is assuming the force is constant. What happens if the force changes, right? If you say that work is force times distance, if the force is changing the whole time, what force do you use? Well, what you might think is if the force is changing all along a displacement, think of a rubber band, right? The force is changing the whole time because the more you pull it, the more force you got to apply. What force do you use? Well, what you're going to have to do is add up force times just a teeny bit of displacement the whole way, and that sounds like an integral. So that's what we're going to do. So let's take this example. We'll do the spring force coming up, but let's do this example. Suppose I've got a force that looks like this. It's just some crazy force with numbers that are just made up. But anyway, if a particle starts at 0 and goes to x equals 5, that force is going to be changing depending on where it is, right? The more it goes, apparently, from the look of it, the more it goes down the x-axis, the stronger the force gets as x squared. All right, so what I want to know is, how fast is this thing going to be going at x equals 5? Okay, that's what I want to know. So it sounds like we need to use our work energy theorem. So the work done by this force is going to be equal to the change of the kinetic energy. And as we've done over and over again, that's K final minus K initial. Again, let's suppose it starts from rest. If it doesn't, that's no big deal. Its starting energy is just whatever 1/2 mv initial squared is. Okay, so what I really want is how much work is done. Now, in this case, the force really is in the same direction as the displacement, so I don't have to worry about the dot product. But what I do have to do is I have to take each little bit of force times each little bit of displacement, and that sounds like an integral. So here we go. So the work done is going to be the integral of f dx. And so this is the integral from 0 to 5. What's the force? It's 0.3 x squared plus 12 times dx. Cool. So this is going to be 0. Oops. Let's just go ahead and do it. This integral is pretty easy. 0.3 times, what's the integral of x squared? It's x cubed over 3. This is going to be 0.1 times x cubed plus 12x. From 0 to 5. Right? Polynomials are pretty easy. And if I do that, what I get is, goodness, 5 cubed. What's that? 125. So that looks like 12.5 plus 12 times 5 is 60. And the 0 doesn't really get me anything, right? So this is going to be 72.5 joules. Okay, neat. So all along this path, even though the force is changing, I can compute that the total energy, the total area under that curve, maybe if, I don't even know, this is some sort of parabola, right? I don't know, it looks like that. But it's plus, I don't know, it's plus 12. Let's see, what would that be? It starts off, so as x is 0, it starts off at 12, and then it goes as 0.3, I don't know, something like that. I don't know. I'm just sketching it. You guys with your fancy calculators and your Google and your internet, you could graph this thing. So if this is force, this is x, right? So the function would look something like this. So the total energy is just the area under that curve. That's the integral. That's what we were taught integrals are. It's just the total amount of stuff under that curve. That's the work done. So all the way from 0 to 5, 72.5 joules has been dumped into the system, a positive. So the energy of the particle has increased 72.5 joules. So it started off at 0. So the final energy is 72.5 joules. So 72.5 is equal to 1/2 mv final squared. Oh, I didn't tell you M. Let's see. What did I? What was M? M's 100 grams. So 100 grams. Everything is always in kilograms, meters, seconds, all that. So this is going to be, let's see, 72.5 times 2 divided by 0.1, and then square root. That's going to be V final. Let's see, if you do that, what do you get? 72.5, what is that? 145 divided by 0.1 multiplied by 10. So that's the square root of 1450. What is that? I have no idea. It's a little under 40 though, right? Because 40 squared is 1600, so it's a little under that. Let's see, if I did it exactly, what did I get? 38. 38.1, so sure enough, it's a little bit under 40. Okay, so even though this force is changing, if I just do the integral and compute the work that way, that'll tell me what the energy dumped into the system is. And notice this is something, since the force depends on x, this is something you really can't do with kinematic equations, because remember in kinematics, the acceleration was constant, right? And here, because the force is changing, the acceleration certainly is not constant. So here's an example of, before in one of the examples, we could do it by either work energy or kinematics. Here, the work energy is way more powerful. This idea allows us to tackle problems we couldn't have done before. Okay, onward and upward.